Hello, everyone. Today I will present our work, Goal-Driven Reward by Video Diffusion Models for Reinforcement Learning. Reinforcement learning has achieved strong results in many control tasks, but in practice, it still heavily depends on carefully designed reward functions. Designing such rewards usually requires domain expertise and a lot of human effort. More importantly, these reward functions often do not generalize well when the task changes. Recently, several works have tried to use expert videos, vision language models, or diffusion models to construct reward signals. However, most of them do not fully exploit generated goal videos as goal-driven rewards. As a result, they cannot effectively transfer the rich world knowledge embedded in large generative models to downstream reinforcement learning agents. Can we use a pre-trained video diffusion model as a goal-driven reward generator for reinforcement learning? Our answer is GenReward. Our framework provides rewards at two levels, a video-level reward and a frame-level reward. First, let me introduce the video-level reward. Given a task description, such as pick up the blue fork, and an initial image, we use a video diffusion model to generate a goal video that describes the desired behavior. Then, we compare the latent representation of the agent's trajectory with the latent representation of the generated goal video. If the agent's behavior is closer to the generated goal video in the latent space, it receives a higher reward. In this way, the video-level reward encourages the agent to follow the overall desired behavior. It provides a coarse but global signal about whether the agent's trajectory is aligned with the generated goal condition video. However, video-level reward alone is not enough. It mainly captures trajectory-level similarity, but it may not provide sufficiently fine-grained guidance for precise robotic manipulation. Therefore, we further introduce a frame-level reward. For the frame-level reward, we first use clip to select the most task-relevant frame from the generated video. This selected frame is treated as the goal state. Then, we use a forward-backward representation to estimate how likely a state-action pair is to reach this goal state. Intuitively, the forward representation encodes the current state-action pair, while the backward representation encodes the goal state. Their inner product can be interpreted as the long-term likelihood of reaching the goal from the current state and action. Therefore, this reward is action-aware. It encourages the agent to choose actions that are more likely to lead to the selected goal frame. Finally, we combine the video-level reward, the frame-level forward-backward reward, and the environment reward to form the final generative reward used for reinforcement learning. Next, let me introduce the experimental setup. We evaluate GenReward on MetaWorld, a standard benchmark for robotic manipulation. We consider 5 medium to hard tasks. To make the setting more challenging, each episode is limited to 256 steps. We compare GenReward with several competitive reward models, including Dense Reward, RoboClip, Diffusion Reward, and Tadpole. The results show that GenReward consistently achieves strong performance across all 5 MetaWorld tasks. In particular, it significantly improves over the original Dense Reward in several challenging tasks. Compared with RoboClip and Diffusion Reward, GenReward also shows clear advantages. The qualitative results on the bin picking task further demonstrate the superiority of our method. In addition, we analyze the effect of different generated video domains. The results show that GenReward consistently benefits from generated videos from different source domains, such as Bridge, RLBench, and RT1. We also conduct ablation studies to understand the contribution of each component. Removing either the video-level reward or the forward-backward reward leads to performance degradation. Overall, our work shows that pre-trained video diffusion models can serve not only as generators, but also as goal-driven reward models for reinforcement learning. Thank you.